through this. Yes, we have the alcohol. Alcohol functional groups are interesting, and I would argue from the student perspective they are awful, and that primary reason being that it has access to all the chemistries. Okay, so if we go through and evaluate all the way down into the nitty-gritty of the alcohol, that hydrogen is possibly acidic, given the proper circumstances. The oxygen has lone pair electrons, which means it could be basic, or, whoops, not E, what's the other word? Or nucleophilic. Because of that oxygen, that carbon is now electrophilic. Right, and then a little bit less so, but still a possibility, this hydrogen out here could potentially be acidic, or over here technically too, that alpha position. Okay, much less so, and you usually need something else to actually get that last one to actually come into play. But that ultimately means all chemistries are accessible to us. And if we're looking at a system where all chemistries are accessible to us, we had better hope that there's some limiting factor.
Not all chemistry.
That limiting, say that again?
Not all chemistry.
I don't know what you mean by that.
Singular electron. It's not going to happen here.
Oh, like radical reactions?
Oh, yeah.
Okay, you're right. It does. We typically don't see radical reactions when we're looking at our alcohols. So we need something to limit some of that, and that's where we would then shift to look at our reagents. Right? And we would hope that we would have a clue within the reagents. If we're falling to the reagents, that can get a bit dicey depending on the format for the particular reagent. Within this unit, okay, our redox unit, that format gets really nasty. Okay? Because what elements are we talking about when we look at PCC? Is it phosphorus and carbon-carbon? It's chromium. Okay? So PCC isn't a reagent that allows us to pick up the chemistry. PCC is the name of the reagent, which means you have to have it memorized. Okay? You have to know that. The CH2Cl2, I don't know why I chose to draw it that way, but I did. Okay, is dichloromethane, methylene chloride. It's a favorite stockroom joke. Is used just as a solvent. It doesn't have a whole lot of chemistry accessible to it. You might say, well, can't the chlorine act as a leaving group? Well, kind of. But then you'd need a strong nucleophile, and we don't have that in our system either. So really, dichloromethane doesn't do much of anything except just dissolve things, which leaves us very squarely sitting on one thing only. What is PCC? Right. And I heard a couple statements. I heard oxidizing agent, which is a good thing to know, and I also heard someone reference chromium. Because the active part of that oxidizing agent is indeed the chromium metal facilitating that oxidation. Okay? So with that information, is that enough to take a swing at what A is?
That's
Okay, so what do we think A is?
Same thing with this ketone.
Okay. If it's an oxidizing agent, what it's going to do is increase the bonds to oxygen. So we'll increase, and I guess we should say electronegative bonds. Since we have oxygen already present, it's usually increasing oxygen, okay, while decreasing hydrogen bonds. So what we're going to do is remove this hydrogen as H+, okay, as effectively H-, so that our electrons can come in and make our ketone. The raw mechanistic detail behind all of that is elaborated on in the slides, and that's when we're looking at the actual structure of our oxidizing agent. I leave that to you to go through and explore and understand what's going on behind it, or you just ultimately memorize it.
So does the dichloroethane do nothing?
The dichloromethane isn't a nothing, it's a solvent. And what does a solvent do?
dissolves the solute.
It just brings everything together so they can interact. That's it. Okay? It brings everything into the same phase. That's all it really does. Okay? And if we're looking at PCC, you probably, I would actually guess you don't need dichloromethane because PCC is in pyridine, and pyridine would probably dissolve the alcohol, though I'm a little bit shaky on that. So using dichloromethane probably isn't even necessary in this case. Okay. Generally speaking, solvents are almost always irrelevant for you, and you don't have to stress about the solvents. What you would have to stress about is if it's written there, you would have to know that it's a solvent and you can effectively ignore it. That's the only kind of scenario that you really need with solvents. If you were in more advanced classes or perhaps with other instructors, they would nitpick solvents a little bit more. We did that a little bit in OChem 1. We aren't going to worry about it, I believe, in OChem 2. Okay? So that sets us up with our compound A, and now we get a branch. Okay? In one case, we run one set of reagents to get to compound B. In another case, we run one set of reagents to get to compound C. What should we do? There was a deep sigh there, so let's lean into that deep sigh. What was that about?
Well, I saw in compound B, there's a yelid, if I had to presume.
Okay. If we look, we've got that carbon double bond to phosphorus, PPH3. Okay. That double bond is typically how the molecule is represented, though we're starting to see some kind of shifts in how people represent that is not particularly accurate to show it as the double bond. Okay. It is actually more accurate to place the electrons on the carbon and show it as the negative carbon and a positive phosphorus. Okay. That does seem kind of counterintuitive because we're now showing charges within our system. Why is that a more appropriate way to represent the molecule?
Because it shows what the chemistry is.
You'd be like, oh, it shows chemistry. Except if we think through everything we've done, we talk about drawing out resonance structures. Which resonance structure are we supposed to draw? The best one, which doesn't show the chemistry. Okay? So that would be an odd swap. If all of a sudden we're going, oh, we're going to do this, so we're going to show the chemistry, but everywhere else we're not going to show the chemistry. Okay? So why should they show it like this? And it's not because it's showing the chemistry. It's challenging.
Because it's named.
No. The orbital that's holding the electrons on the carbon is effectively a p orbital. Okay, that's what's allowing that resonance. Okay, but what p orbital is it? Are there different p orbitals? Yes, there are different p orbitals. It's a pretty straightforward question. No, that's an sp3 orbital.
P3 would be the open one.
I asked p orbital.
P3 would be the open
P3, I don't know what P3 is.
one. I don't remember my fucking shit.
P3 would suggest there's 3 electrons in your p orbital, and not in an orbital. In the orbitals, sure. The 2p orbital. Why is it the 2p orbital? Why did you say 2? Where the hell did 2 come from? Carbon's in the second row. This is too stupid, Mike. This can't. Yeah, that's it. Carbon's in the second row. Its p orbitals are in the second row. It's the 2p orbital. For phosphorus to be making that pi bond, phosphorus also has to have a p orbital. Where's phosphorus's p orbital? Third energy level. Okay. There's a significant size difference, effectively, between our 2p and our 3p. So much so that the overlap is relatively minimal. And if the overlap is minimal, do you get a bond? No. That's one of the reasons why we talk about the Wittig in the yelid form, where we see the charges, because we don't get a lot of orbital overlap. Therefore, we can get rotation, all that other fun stuff, okay? And it makes sense to show it as the negative positive because the bond isn't actually there. Okay? That's a pretty esoteric, deep thinking kind of thing, but I think that's kind of neat to at least address, so that's why we're talking about it. Okay? So cool. That gives us a chemistry. We can lean into it on the chemistry side. We've got a negative carbon, the phosphorus. What could possibly happen?
The carbon would act as a nucleophile.
The carbon acts as a nucleophile and needs to react with what?
Positive.
Where's there a positive?
The carbon connected to the oxygen in the substrate.
Okay. Our carbonyl carbon. Okay. So our negative carbon can come in and attack. We would then break the pi bond between the oxygen. Then what happens? Then the oxygen is charged, yeah? Yeah. Oxygen attaches to the phosphorus. The phosphorus doesn't like it, shuttles the electrons back down to form a carbon-carbon pi bond. That exceeds the octet on our carbon, which kicks the electrons between our carbon and oxygen up to the oxygen. And now everything's split. I just got two people going wide-eyed on me, so let's draw that a little bit. And it sounds like Abby was also going wide-eyed. I just couldn't see her face. There's our carbon. There's our phosphorus, PPH3 with the positive. There's the negative. Okay. If this negative comes in, it exceeds the octet on our phosphorus. These electrons rotate down to create the pi bond. Then these electrons rotate up to the oxygen to satisfy everything, which then means the end result of all of that glorious nastiness. And I guess I can attempt to color code here. Our carbon, we'll come back to that. Of course, I'm saying all the little stupid hand touch lines on it. Let's clean some of those up. Okay, and we'd have that. Note, I'm just showing it as the red carbon. How many carbons were supposed to connect? How many carbons are connected to that red carbon all the way up? And you'd be like, well, it's just one, Mike. It's just one, Mike. Did I draw it correctly? Look at what was given. Well, I'm not even concerned about that. We've got to make sure we've got all the carbons from that first step. Did I do that correctly? Yes. Okay, if we look at step 1, reagent 1, there is only one carbon there. Okay, so far, yes, I am correct within my assumptions and all my fun drawings, and that looks legit. Okay, officially, I shouldn't show that as a carbon. I should probably call it a CH2, or just delete it all together and just show the double bond floating out into nothing. That is step 1. Now you have to do step 2. And what do you see in step 2?
Something we don't normally work with.
Hydrogen gas.
Okay, I can kind of accept that. It's hydrogen gas and a metal. What does hydrogen gas and a metal do? Reduces the pi bond. Ta-da! And that's it. Okay. You can see hydrogen in nickel, you can see hydrogen in platinum, you can see hydrogen in palladium. Okay. Sometimes you'll see hydrogen and palladium with something. Okay. That with something is usually in reference to a catalyst that prevents the reduction from going all the way. But if we're looking at an alkene, there's only one reductive step. Okay? So you typically won't see that with something. Okay? That something can be referenced as poison, barium sulfate, calcium carbonate, barium carbonate, okay? Maybe even calcium sulfate. There's a variety of things that can get added in there. And what that is doing is trying to only allow one reduction. Okay? That one reduction is when we're talking about alkynes. And we only want to reduce the alkyne one step. And if we reduce the alkyne one step, what do we end with? An alkene. Okay? So we wouldn't expect to see that reagent here, because if we added that extra stuff, what happens? Well, nothing. That extra stuff only acts on alkynes, not on the alkene. Right? That's the whole point of it. Okay? So if you're looking for that hydrogen gas, you see hydrogen gas and a metal, you should immediately think reduction. Okay? The next kind of tricky part that could potentially go with it is reduction of what?
An alkene.
Alkenes can be reduced, yes. Can other things be reduced with hydrogen gas?
Yes.
Yes. What other things? Aldehydes, ketones, alkynes. Okay. What do those all have in common? Pi bonds. Okay. So that particular reagent is horrendously unselective as far as we're concerned. Okay. So if you pump hydrogen gas with a metal and there's pi bonds, you destroy the pi bonds. Okay. It is a little bit more nuanced than that. I think our textbook goes through and actually shows a table and is like, okay, if you have hydrogen and platinum at 300 psi, referencing the hydrogen gas, it reduces this functional group. If you switch it to 200 psi, it's slightly less pressure. So now it can't reduce that other functional group and it reduces this other one. So you can change some of those conditions to force certain reductions over others. Okay? But it's a relatively crude system, not particularly great, which ultimately means we don't care. If you're seeing hydrogen gas and a metal, you just reduce the hell out of everything. Okay? Cool. So that got us structure B, right? I think it was called structure B. So there's structure B. There's structure A. Come on, pencil. There's structure A. So what about C? Okay. We could go through and look at this structure. We have lone pairs on the nitrogen, which could go through and attack our electrophilic site. Why not the negative charge on our oxygen? Full disclosure, I don't like this answer. Which one's the stronger nucleophile, a negative oxygen or a neutral nitrogen? Okay, so you're telling me what it does. I didn't ask what it does. I said which one's the stronger nucleophile, negative oxygen or nitrogen?
Hydroxide is stronger.
Oxygen's the stronger nucleophile. So why doesn't the oxygen attack the carbonyl? It does, and it creates a hydrate. The hydrate is naturally unstable and falls apart, ultimately back to the carbonyl. Doesn't take us anywhere particularly productive, useful, or new. The nitrogen, on the other hand, does. Okay? I am not drawing the mechanism in this class right now. I've drawn it once in the stupid video, and it is stupidly long to go through. Okay? Ultimately, there's really 4, I think, critical mechanistic steps. Everything else, the other 16 steps, that's an overkill of a statement, but close enough, are acid-base reactions. You take a hydrogen on, off, you put a hydrogen on. Take a hydrogen off, put it on. Okay? So ultimately, what you should do with this, right, is not worry about the mechanism, because that mechanism is stupid long. And as we addressed with the aldol, we had a conversation, I think it was you and me, with acetals. Mm-hmm. Yeah. With the acetal, we encountered that neutral structure with the hemiacetal, right? Like, well, what am I supposed to do here? It's neutral. Shouldn't I stop? No, we don't stop. We have to continue. Why? There's some energetics, extra things that go along with that are kind of hidden from us within our system. Right? If we go through and look at this reaction, the NH2 with that carbonyl, we hit probably 2 or 3 neutral structures through that mechanism. And it continues. Okay? And it continues to pass through those steps. Okay? So if you're just running this as a mechanistic explanation to try and get through, you have to break through 2 or 3 pretty solid barriers of, shouldn't I stop now? Right? And that's a hard system to do. So what I would argue you should do instead is memorize the outcome of this reagent. Whoops, as I erase the reagent. Okay? I have no doubt that somebody has memorized the reagent or the outcome of this reaction, so can you tell me the outcome?
It just completely removes the oxygen, replaces it with 2 hydrogens.
We toast the alcohol or the oxygen.
So
Right.
it just
It-
reduces.
It is a reduction reaction. It is a reduction reaction that's similar in effect if you will, back to our hydrogen and our metals, it fully removes that functionality. Right? And it takes us all the way down to, in this case, just the raw alkane. Okay? So there's an interesting question then. If both of them are reduction agents, H2 and the metal versus the NH2KOH, why do I need two different reducing reagents?
Well, one adds a carbon.
No. So in the other reaction, like, oh, but it added a carbon. Did the reducing reagent add a carbon? No. The Wittig reaction added a carbon. Okay? So you're right. To get product B, we added an extra carbon. That was different, but we added an extra step. If I had just done H2 in the nickel, what would have happened to my carbonyl?
Would have been reduced.
It would have been reduced to what?
Alcohol?
An alcohol, not fully an alkane. Okay? So that reagent doesn't do the exact same reduction pathway. It does something slightly different. Does that kind of make sense? That's why we need multiple reagents. Okay? On top of which, what did we say the H2 in the metal would do?
Just pi bonds.
Reduce pi bonds. Which pi bonds?
Any.
Any. If our starting molecule happened to also have another pi bond in it, and I use the H2 in the metal, what happens to it? It's gone. If I use this NH2 reagent, what happens to it?
Still there.
It's still there. Okay? So the the N2H4 reagent hydrazine is selective for carbonyls. The H2 in metal, wherever it went, H2 in metal, is unselective. Just destroys everything. Okay? Depending on what you're trying to do within your synthesis, you may not care whether it's selective or unselective. But generally speaking, we tend to favor selective reagents. Okay, kind of makes sense? Okay. For the sake of my exams, I would give you the structures. I would say this N2H4, KOH, and heat. Okay? I would give it to you like that. Okay? The ACS may not do that. They might do something else. Okay? Which kind of has to do with what we just talked about. If we push through the mechanism, we hit 2 or 3 neutral products that we had to continue to push through. Do we like pushing through neutral products? No. He said, well, why should it continue? Okay. Well, it continued. The reaction continued, which means the person that went through and discovered, hey, it continues, gets to name the reaction. This is what's known as the Wolff-Kishner. That's what I was pausing on. Kishner? I don't know if there's a C in there. There's not? Okay. So you all can spell better than me. The Wolff-Kishner reagent. Okay? So ACS level, you should be memorizing both the name and the reagent. Okay? I would not spend the time to memorize the mechanism. Is it a mechanism worth driving through and practicing on your own? Yes, I do think so. Okay? And it's a pretty special reaction because one of the byproducts that it produces, I'm going to erase that double bond because it's kind of bugging me. One of the byproducts it produces is N2 gas, and that's the biggest driver for that reaction. Okay, N2 gas is extremely stable, so as we run this reaction, it offloads that nitrogen gas. That's one of the reasons why we pass through all those neutral intermediates. Because if we continue to pass through, we end up with something that's incredibly stable. That's the driving force that allows us to drive through all of those individual mechanistic steps. Okay? I'm going to add one more thing. While it has, again, exaggerating 20 mechanistic steps, does that make the reaction slow?
No.
No, okay? And the only reason I'm mentioning that is in the fundamental class, it's something I have to address too. People are like, oh, it has 2 steps, so it's slower. That doesn't make it slower, okay, than a 1-step reaction. It just means there's 2 things happening. You could have those 2 things happen faster than that one thing. So don't start making comparisons between reactions to say which one's faster or slower, okay, based off the number of steps, because that can be very, very misleading. Okay? Kind of, sort of? Ivan, I think that was your question. Are you good?
Yeah.
Is that all it asked? Was just those structures?
Yeah.
Okay.
Does the H2 and the hydrogen gas and the metals have any colors?
When it's nickel, I think they call it rainy nickel. When it has H2, a metal, and something else, they do add another name. I want to say Lindlar's catalyst, though I could be wrong on that. I think I get Lindlar's and rainy confused. And you'll see poisoned as a term. Yeah, poisoned. You've prevented it from fully reacting. That's how I see it. Right. So there are a lot of names that get dropped through this particular reaction, or through this particular chapter. Other questions?
E, on the opening exam.
And no offense, Ivan, I'm going to pause on you for a second. Does anybody else have questions? Okay. What did you say, D?
E.
E. Whoop. And I think I already heard people like, ugh. Isn't that exactly what we want to hear? Right? So remember how I talked about spectroscopy is going to be a thing that we have to address and remember all the way through? And then you're like, but it didn't show up on exam 1 because Mike forgot. I forgot once, largely because it was not on the practice exam. Right? And then every semester, I continue to forget that spectroscopy needs to be added into exam 1 because it's not on the practice exam. Here's the reminder, which means, guess what? It's on this exam. Okay? It's now clearly here. Looking at the practice exam, I know that we're supposed to be talking about it. Okay? So yes, it is something you should be aware of, and it should show up on the exam. Okay? So we've got a lot of text to sort through. Okay? We've got a lot of structures, or a lot of spectroscopy. We even have a reaction there. Okay? For the sake of speed, what you could attempt to go through and do is just try and target as much partial credit as possible. Okay? So there's that internet meme with the guy waving around lightsabers and saying, did not read. Don't read it. Just look at the stuff you know you need to do. Okay? Look at the bottom. Why would we look at the bottom first?
Because it's where everything is.
That's the easiest. That's IR spectroscopy. Okay? We also have HNMR. And then we also have a chemical reaction. Okay? So we've got lots of kind of context within this. Okay? We have this A and B, so without even reading, okay, we probably need to figure out what A is, and we probably need to figure out what B is. Okay? The spectra could be referencing one of those. It certainly doesn't reference the starting material, because why would I give you spectra for the starting material? That doesn't make any sense. Okay? The whole point of spectra is to figure out the structure. So if we look at the IR, what do we see?
It's on 1700.
We got a carbonyl screaming at us right there. Okay? What does that suggest about the reaction? If I go up to structure A had better have a carbonyl inside it. I've now provided some context. Okay? Minimally, I've analyzed the IR, and I've provided a guess to what the structure could be for our final answer. Okay? I would argue you should lean into IR just a little bit more. You analyze the big piece. Okay? But when we do spectroscopy, you're supposed to fully analyze. What else should you be picking up out of IR? Okay, I accept CH. What hybridization is that? That's sp3, not sp2. Less than 3,000 is sp3. Greater than 3,000 is sp2. Okay? And since it's sp3, what does that suggest about my reaction? There's no more alkene. So I could now go through based off of just the IR alone and say, ta-da, there's answer A. IR, there it is. Done. Move on. Okay. Are we right? No. Probably not. Yeah, no, you're not. Okay. How would I know we're not right that fast? For the record, I didn't read the question yet even.
You interpret the HNMR?
I looked at the HNMR. Okay, and you said interpreted. Does that mean I figured out what the structure was? No. What did I interpret in the HNMR to tell me that that's not the final answer?
Number of hydrogens. Unique hydrogens, I should say.
The number of unique sets of hydrogens. And how many numbers are there? 4. And if I look at my structure, how many do I have?
Not 4. 3.
I have 3. Which minimally means
You fucked up.
I mean, that's a fair interpretation. I was going for something more productive than I just screwed everything up.
We're missing a carbon.
I have to be missing a carbon because there's not something else I'm going to be able to do to change that out. Okay? So within this, I now might lean into my HNMR a little bit. I've got 4 unique signals, okay, which means 4 hydrogens, okay, or 4 types of hydrogen. What's the next thing I should interpret?
The strength of said signals?
Nope.
What?
Chemical shift.
Fuck.
Okay. Okay. And I would actually kind of agree with that statement, a little bit off kilter there, okay, as per usual. Okay. If we look at this chemical shifts, they're all really, really, really low. 0 to 2 is alkane. We've got alkanes. 2 and higher is in the everything else range, so we don't get a whole lot of context there. Ideally, we've spent some time looking at some spectra for carbonyl compound things, and we would start to trigger that if we have a hydrogen that is alpha to a carbonyl, that hydrogen shows up about 2.1. Okay? Why is that useful for me? I can go through and see that I have 2 signals that are sitting in that range. Okay? My structure isn't going to fix that because I do still have those 2 signals. Okay? So the chemical shifts, I've really got 2 alkanes, and I've got 2, we'll call it alpha carbonyls. And I just decided to randomly erase parts of it. Okay, what's the next thing we should look at?
The 0 to 2 range?
We just addressed the 0 to 2 range. That was our alkanes.
Yes. Oh, do you mean now do we get to look at the strength of the signals?
So now we could look at the strength of the signals, and it's less strength of the signal and more relevant to the area underneath the curve, okay, which should be given as a number underneath or these 2 H's next to them. Okay, those are representing the integration. Okay. Depending on how ACS has decided to format the test, they may or may not give you the integration information, which I think is absolutely horrendous. Okay, and I think enough people have complained to ACS that they may be starting to fix their mistakes in that respect. Okay, because what they've expected you to do in the past is look at the height of the signal. Okay, the height of the signal does not directly correlate to the area underneath the curve because you can have broad curves that are very short. A broad curve that's short has a larger area underneath it. Okay, so it's something to consider. Okay, when we're looking at just carbon and hydrogens, those peaks are all relatively sharp, so we could probably get away with looking at the height of the peak, okay, as long as we acknowledge that we're stacking them. So if we look at this first 3H signal, what we would have to do is stack all 3 of those peaks into one signal. Then we could compare the height of that signal to, say, this one singlet signal. Does that make sense? In this case, we don't have to do that because someone was kind enough to go through and tell us the integrations for each of these.
Who you hired to do that? Because I know you were. Like,
Yeah, I'm a horrible person. I would never give that information out. Okay? So if we look at that integration information, what do we have? Okay. Well, we have a 3H in that alkane range. What would that mean?
you have CHSP3.
We have a CH3, okay, that is likely next to a carbon that is not the carbonyl. Okay? We know it's not the carbonyl because if it was the carbonyl, that would give us the chemical shift up at the 2.1 range. Okay?
Oh, I see what you mean.
Next signal is a C8 or a 2H, which means I likely have a CH2. Okay, it's shifted a little bit higher, so it could be getting close to that carbonyl, but I would argue it's probably not touching the carbonyl yet. Next thing I've got is a CH3.
That's definitely touching the carbonyl.
That's definitely touching the carbonyl because it is shifted way higher. Okay, so we're looking at a CH3 next to the carbonyl. Okay, the last thing we've got, again, a CH2 that is again shifted way high, which would suggest it's next to the carbonyl. Okay. With that information, would we be able to process out a potential structure?
Yep. Arguably, you could have done it without a lot of that stuff if it wasn't for points. But
Yeah.
you just add another carbon on the right side.
Okay. And it's figuring out where you would add that other carbon that comes into play. And so you could guess and check your way through because there aren't very many options. Okay, so we didn't have to get into the integration to pick this out, but if we match our initial guess, okay, we've got our CH3, yep, next to the carbonyl. That aligns with our red on the left side of the structure. If we move to the right, we have a CH2 next to that carbonyl. That makes sense, so that should be that green one. Okay, I need a CH2. I haven't even addressed what's near it yet. I'm just saying a CH2, okay, that isn't next to a carbonyl. Okay, so that could be, what color were we? Purple here. But then I would need to account for my new blue bond, which means dropping that blue bond out there. Now I've got the potential to explain that. Okay? I've processed through those pieces. Okay? And I'm adding kind of information as I go. Okay? Officially, we haven't fully solved the NMR. So you got to decide. How many points do you think the full interpretation of the NMR is going to be? You've done 3/4 of it. We also have the IR. We also have probably figuring out what structure A and B are. How many points do you think it's worth for the multiplicity?
Maybe one.
Maybe one. Is it worth your time for 1 point? No? Fine. Screw it. Move on. Hope for the best. Okay? But we're in class. We can't say screw it, move on. We got to go look at it. Okay? So where do you want to start? Blue or green? Or red or purple? I guess it doesn't really matter. What's that? Blue. Okay? The blue has 3 peaks. If we have 3 peaks, what does that mean?
You got 2 neighbors.
That is 2 neighbors. Which means my CH3, my blue CH3, needs to be next to, whoops, and I won't color them specifically, a CH2. So we'll call those in black so we know we haven't necessarily identified them. Okay. What about the purple one? How many peaks do we see?
A bunch. Was that 5 or 6?
Is that 4, 5, or 6? Yes. Okay. This is where you've got to go through and look real carefully at it. Yes, we have a little blip. 1, 2, 3, 4, 5, 6. You're like, that little blip counts? Yeah, welcome to spectroscopy from last semester. Yeah, it counts. So there's 6 peaks. What does that mean?
5 neighbors.
6 peaks equals 5 neighbors. 5 neighbors, if we go now to our purple structure, okay, how can we get 5 neighbors?
Next to CH3 and CH2.
I need to be next to a CH3 and next to a CH2. Okay. What happens with the red signal? It's 1 peak. 1 peak equals 0 neighbors. I could go through and look at my red structure. Do I have any neighbors? Nope, I don't even have to modify anything. It's already set. Okay, how about the green one?
3 peaks.
3 peaks equals 2 neighbors. Okay, there's only one direction I have to go to place hydrogens out there. Okay. We could now go through and reconcile this extra information with our splitting pattern back to our structure. We start with the red one. It's a CH3 next to a carbonyl and no other hydrogens within 3 bonds. Is that true? Red one.
Yeah.
Yes. Green one. Okay, it's next to a carbonyl. Yes, and it's next to a CH2. Is the purple a CH2?
Yep.
Yep. Purple one. It's a CH2 between 2 carbons. Yep. On one side I have a CH2.
Yep.
One side, the other side I have a CH3. Yep. Blue one. I have a CH3 that's next to a CH2. Is it next to a CH2?
Yep.
Yep. What does that mean?
That's right.
Hallelujah. There's the structure for A. Okay. Again, did not read any words. All we're moving through is based off of the predicted things that we could expect to kind of put through this. What's that?
1-year-old couldn't interpret an IR spectrum.
He's pretty bright.
Oh, that's your 1-year-old. Oh, okay.
Wow. It was my 1-year-old. He's not a 1-year-old anymore.
He's just a big 1-year-old now.
He's an 8-year-old now. Wow. Man alive, really?
Mike's realizing he's old now.
Yeah.
That's
And-
what made you think you're old?
Yeah.
Have you looked at your birth date?
No. God. Sorry, I did actually start to read it. That's why I got lost. I was like, he fell ill. I was like, I guarantee he was sick at home when I had to write this stupid question. Or he brought me all his notes of saying, look at what I drew. And it's just a bunch of weird scribbles being like, look at the school bus. Like, what the hell are you talking about? I'm recording this. God damn it. Oh, he won't know to check, at least for another 30 years. What are we doing? Missing thing, B. Right? Again, without even reading the rest of it, we could look at it and say, well, B is something labeled there. Okay? If it's labeled as B, we could very likely be being asked to tell us what B is. What is the reagent that would allow this to happen? Okay? Again, I don't know yet, because I didn't read it. Okay? But that's very likely. Okay? If we go through and do this, that B reagent needs to be what part of my product?
This extra carbon.
What's the extra carbon?
The blue one.
The blue one. Okay? The reagent has to have that CH3 in it. So if I'm looking at B, it needs to be a CH3. Okay? What's the problem with just saying CH3?
Doesn't tell you anything about how it reacts.
True. Octets. It's missing its octet. Is that a positive CH3, which is now getting to how it reacts, or a negative CH3? Okay. Is there a bromine connected to it? We're missing that octet. We need to provide some more context behind where that CH3 is coming from. To figure that out, we would have to go back and look at our starting material and say, well, where did it react? Okay, so if we look at that carbonyl, and now aggressively did not read, as we erase all of that. I want my CH3 to react here. So what do I know about that spot?
A negative charge would be better at that spot.
Are you saying that that carbon is negative?
I'm saying that
That this is negative, or that the thing coming in is negative?
I'm saying that the red one would be negative.
The red one would be negative, which means we want our CH3 to be positive.
Yes.
Okay, why do you think the red one is negative?
Because it has less stuff around it, less electrons.
Cool. We could push that less stuff argument, okay? And that's not a horrible argument. It's unfortunately wrong, but that's not a horrible argument, okay? Yes, that's where we want the chemistry to happen, but before we start talking about where the chemistry happens, we need to make sure that the rest of the molecule doesn't somehow affect that position.
Yeah. You go ahead and say resonance, yeah. Yeah, say you're fucking lying. Yeah, go ahead.
When we look at that overall molecule, where should our primary focus for chemistry be?
Carbonyl.
The carbonyl. Why?
It's the most reactive thing on that.
Why is it the most reactive?
Polar pi bond.
It is a polar pi bond. That polar pi bond is going to take the electrons out of that pi bond and shuttle them up to the carbon. I'm not going to draw out all of our structures, and I'm trying really hard not to use that word. Okay? Generating a positive charge there. Okay? That's where the chemistry should happen. Okay? It didn't happen there, so I don't care necessarily, but what I want to see is why the chemistry would shift. So is there something else I could do with this now? Is there something I could do to stabilize that positive charge? We have a nearby pi bond, and we could shuttle that pi bond over. If we shuttled that pi bond over, what would we produce?
Positive charge at that
A
position.
positive charge at that position.
Yeah.
Okay? Which suggests the thing coming in attacking needs to be negative. Okay? So, again, the logic of, I think that's negative because least steric hindrance, that makes the most sense. Looking at the alkene pi bond on its own, 100% true.
It's like the fifth time I've done this.
We have to acknowledge the rest of the structure. Okay? Particularly if the rest of the structure is more reactive. Okay? We have to think through those secondary considerations. Okay? So that means we need a negative carbon.
Lithium CH3.
Okay? So cool, negative carbon. We need to put something in there to counterbalance it, so we could drop in a lithium. Okay? Let's backtrack to all those drawings that we went through and did. And if we consider all the things that we drew out, we said the oxygen was partially negative. What was the carbonyl carbon? Partially positive. Okay? And we said that terminal spot was partially positive. Okay? That's what we saw within those. Okay? This should establish a potential issue. We want our negative carbon to attack what? A positive carbon. How many positive carbons do we have? 2. Which of those carbons is more positive?
The one on the carbonyl.
The one on the carbonyl, because of the polar pi bond with the oxygen connected to it. So if I'm going to throw my negative carbon at this, where's the negative carbon most likely to go?
The carbonyl.
To the carbonyl carbon. Okay? And that would be a situation for a kinetic product. We're trying to neutralize that positive charge as fast as humanly possible. And if I throw in a wicked strong negative, that's exactly what it's going to do. Do I want it to do that? No, which means what should the negative be?
Not wicked strong.
Not wicked strong. So now I'm stuck in this weird gray box of, well, what's not a wicked strong negative, considering that carbon can't stabilize negative charge? Aren't they all wicked strong?
I mean, you just gotta attach something that's less electronegative than carbon to carbon, right?
Put a hydrogen on there. It's a nonpolar covalent bond. You have no electrons on the carbon, and you have no nucleophilic characteristics.
Why not? Like, I don't know, phosphorus or something. I don't care. That's one thing I know that is less electronegative than carbon. That's all about a line.
Phosphorus was also come in with a lone pair of electrons, and that lone pair of electrons would likely act as your nucleophile instead of the carbon.
Would that more likely act as a nucleophile compared to the?
You have available lone pair electrons on
and
the
since
phosphorus.
phosphorus is less electronegative, it's gonna throw those out there, yeah.
And if you're thinking like, I don't know, like this sounds kind of wicked impossible. That's kind of because it is wicked impossible, which is why somebody
Is there a name?
attached their name to it.
It's not Hoffman, is it?
No.
No, thank God.
It's Gilman. It's not Grignard, because Grignard is wicked strong, just like the lithium, and it would attack the carbonyl. What we need is the Gilman reagent. So if you go through and look at this and you're like, I need a negative carbon, I happen to remember it needs to be Gilman, but I don't know what that is. You've provided so much context here. How many points do I take away?
None.
That's going to be really hard. Okay? And I would bet maybe half a point. I mean, with everything else up there, I might even be less than that. I might be like, I can't give you full credit because you haven't answered the question. Here's 6.9 points.
Oh, of course.
Okay? Which would be really obnoxious. But hey, you know, that's where it is. So what is the Gilman reagent? There it is. It's with copper. And if all you gave me was copper and the CH3, I would accept that. That's provided enough context, put me over the edge. I'm not going to deal with fractional points. But officially, when we're looking at the Gilman, that B is starting to bug me a little bit, a little too close to it. Okay, because that's not part of it. Okay. You take the organolithium compound, a CH3Li, and you react it with copper iodide. I think it's copper iodide. The copper inserts itself into that bond, keeping the carbon nucleophilic, but because the lithium is more electronegative than both magnesium and lithium, it creates that carbon and makes it slightly less negative. Just enough so that we switch from a 1,2 attack to a 1,4, which is why it's really important to know the Gilman reagent. Right? Because it's differentiating between that kinetic versus thermodynamic, 1,2 versus 1,4, all of that fun stuff. You should really know the Gilman reagent because it does that odd chemistry. Right? The Grignard, as neat as it is, I would argue isn't odd chemistry and isn't worth memorizing it as a name. Right? But the Gilman doing interesting stuff should be memorized. Questions?
Well, on a different question, yeah.
Well, yeah. Let's go back to this first. Are we good with everything that's up there?
So, like, where's the copper attaching itself? That's what, like, could you draw it out? Like the lithium copper CH3?
It's
Is it
going to
just-
be anticlimactic.
No, I know. I'm not acting like it isn't going to be anticlimactic. Oh, okay, gotcha. Didn't expect that, but yes.
Yeah, I think that's all it is. Yeah, and I think that's all it is. And before, no one yells at me online because no one watches the videos, but before anybody yells at me online, I'm actually just guessing, just vaguely off of what I remember about that reagent. But it is something you can look up to see. And yeah, that's, the carbons coordinate the copper, and the lithium is just floating as a random counterion. It's a spectator. Yeah. Questions about it? Can I delete everything? Is that a yeah? No, you're still drawing. Right. Officially, what we should do is go through and actually read the question. Make sure that we actually answered it, but I believe we did. Okay. Based off of what I'm seeing, show full analysis of the H and MR, probably and the IR. which probably says predict the product of the reaction and use that information to determine the reagent B for the synthesis of that product. Okay. Which is all in bold. So if you're looking at a big paragraph, what should you potentially do? Test taking strategy.
Read the bold. Forget
Just
the
read the bold and forget the rest. Okay. If someone's being kind enough to bold it, it's probably because they think that part is really important and the rest is boring. I don't know.
You can let Barbara know when you finish the
7 years later.
Irish pretend. Yeah, it looks like we did all that. Okay. The next part that I want to kind of layer into this that we want to be aware of, okay, which goes to the practice test. Answering this question is not useful.
Why not?
Okay. What are the odds you see this question on the exam? Okay. So knowing how to provide the answer to a question isn't useful. Knowing how to provide the explanation of all the work on how you got there is useful, which is why we talk through all of that context. Okay? That becomes the important part. The next step that you should be doing as a student is looking at this question and being like, Mike's a lazy SOB. How can he change this question very quickly with just a few swap outs and ask the same question without asking the same question? Ideas?
Add another carbon or two to the initial chain, just to fuck with the
Okay.
HNMR one.
We could make the HNMR more complicated by adding more carbon. Instead of just adding a CH3, we add 2 or 3 carbons. Yes? Where did our carbon attack? On the end. Because there was another partial positive, maybe we should have it attack not on the end. Maybe we should have it attack the other position. How would that change my spectra? What would I expect to see? Okay.
Oh, you.
Very subtle change to the overall question. Big change in the potential output for our multiple or our spectra. Okay. What would that do? What would that allow me to think about? What should I be seeing in the spectra
Well,
if that's the case?
Shouldn't be seeing that peak at 1700.
Okay. You've now projected what a shift could be. Okay. Very quickly, by analyzing just this question, you could go through and, well, if it attacks the carbonyl, I don't have a peak at 1700, which means when I look at the IR, ta-da, it's not there. Very subtle amount of work on your end, but sets you up for almost instantaneously being able to look at a deviation of this question and be like, I know what it's doing now. Because you've already answered the question that hasn't been asked. Kind of make sense? Push on this even further. When we talk about reacting our carbonyls as electrophiles, what did we react them with? Okay, so in silence, I'll give you the easy answer. With nucleophiles.
Oh,
Okay?
it's more trying to analyze
What
it's
nucleophiles?
the carbon.
We had a carbon nucleophile, right? Gilman, yeah, that was a carbon nucleophile. Cool. Was that the only nucleophile we reacted with our carbonyls?
We react with other carbonyls.
We reacted them with other carbonyls, which was technically also carbons.
Oh, yeah.
What other nucleophiles did we use?
Oxygens.
Oxygens, nitrogens, hydrogens, and bears, oh my. Okay, so what you could think about was, okay, well, if it was hydrogen, now how would the hydrogen react? Okay, you might push on that even further and say, well, this is that conjugated alkene carbonyl. That's only looking at this 1,2 versus 1,4 differential. What are the reagents that center around those two conversations? Okay. So that if I lockstepped this reaction, you could now say, here are all the reagents that would potentially react with this, and this is how they would react. Okay. and thinking of that, this is how they would react. I know that sounds daunting, but what you're doing is now creating a list of all the reagents that we talked about. You mean all the reagents that you're responsible for on the test and answering questions? Yeah. You mean like you're studying for the test? That's a pretty cool idea. Let's do that. Yeah. That's that thought process that you should be projecting outwards to figure out what you don't know so that you can be prepared for it when it hits the test. Kinda, sorta? Okay. What's next, Simon?
You just give it up. Just ask me.
Well, you all gave me a solid 5-10 seconds of nothing, so.
Oh, what the fuck is that?
Okay, so yeah, and this question is almost designed for that exact response.
Just delete it, we don't need it.
Okay, and this is where it starts.
Let's see, circle that.
Everybody goes, well, I don't understand why we need organic chemistry. Organic chemistry is stupid. Well, here you go, dude. This is organic chemistry. Ta-da! Okay. This is a super relevant reaction to looking at biochem, a biochemical pathway. Okay? And if you're really familiar with your biochem, what can you tell me we're starting with?
Glucose?
Yeah, we're starting with glucose. What are we looking about? We're looking at glycolysis. I think it's glycolysis. I honestly don't know my names in biochem. I think I'm too far from the recording, so maybe I'm okay. Right. And what we're breaking it down into is the two decomposition. The decomposition products of glycolysis, right? Which are pyruvate and I think it's ultimately just 2 pyruvates. Right? This is that process. So if you're going to go into biochemistry, you will potentially, look at this, why do I say potentially? Right? Biochemistry as a class is heavily dependent on organic chemistry. But how many biochemists like dochem? Very few. In fact, if you asked biochemists how relevant biochem or organic chemistry is, oh, it's not relevant at all.
Isn't that what runs everything they do?
Everything that is happening in biochemistry is based off of organic chemistry. You've just decided to ignore that part of it. That's okay, I get it. I ignore the entire field of biochemistry. So like it's fair. Right? But just saying it's not relevant is an entirely different animal. Right? So what we are looking at here is the process for how we could potentially break apart glucose in the enzyme. Right? So there are some terms floating around in here. You see LYS. Okay, Charlotte, you at least recognize glucose. What's LYS?
Is it Listerine?
Which is unfortunately very, very close. It's not Listerine. Lysine, TYR.
Oh, I think that's isn't that
Tryptophan. Those are
a Viking god?
amino acids.
Oh.
They're amino acids in the active site of the protein that processes glucose. They're there to facilitate the transfer, usually of just hydrogens, back and forth, so that the molecule falls apart on its own. Okay? So we take advantage or leverage acid-base chemistry to force all of these chemical reactions to happen. Right? So if we go through and look at these pieces, right, all you need to do is circle the atoms and label how it is involved in the mechanistic step. Nucleophile, base, acid, electrophile.
Oh.
That's it.
Oh.
Right? It is made a little bit more challenging. Right? The nucleophile would be the thing donating the electron. So that would be where the curved arrow starts. There are no curved arrows. Okay? Which would mean you would need to be able to interpret what's happening within that. Okay? So there are pieces of information that are hidden within this that you have to be able to process and look at and evaluate. So you're looking beginning to end for each of those individual things. And when I say beginning to end, I want to be extra clear. This is beginning to end. I ignore all of this.
What?
Okay? Because I need to know what's happening in that step. The rest of it is irrelevant. Okay? Once I've answered that step, what can I do?
Then go to the next step.
Now I can move to the next step, and the rest of it is irrelevant. Okay? So you're slowly piecing through and processing what all of those little bits of things are. Kind of, sort of? Okay? Should we go through and start to work on it together?
If you'd like.
I'm tempted to say everybody go to the boards, but I think that's an awful idea because you'd have to redraw all these structures. Okay?
I don't know. This seems relatively simple.
It is. I think it's personally relatively simple. It's easy to get lost in all of those
But
structures.
you're also kind of an
Right.
ass, so it's like.
That's fair. Okay. So let's start. What's happening here? What do you notice is changing?
Nitrogen gets a single bond with the oxygen, and oxygen loses a pi bond.
So we could talk about that bond. Okay. That bond to the nitrogen has formed. That's a new bond. Like, oh, that's a really long bond. Who cares? Okay. And what happened?
Oh, and the oxygen lost a pi bond.
That pi bond broke. Okay? So how could that happen? What would have to happen evaluating either the red or the blue?
The nitrogen must have been the nucleophile.
The nitrogen had to share electrons with the carbonyl, causing the pi bond to break up to the oxygen. How do I know the electrons went up to the oxygen?
Because nitrogen lost its lone pair.
The nitrogen losing its lone pair helps to explain why the nitrogen attacks the carbonyl.
Oh,
How do I know that red arrow goes to the oxygen? Okay? So one option is looking at our product and saying the product shows that that oxygen has two lone pairs. Except one of the things that I believe it says is sometimes we're missing charges in lone pairs. So relying on that isn't a good option. What else could you rely on to explain that red arrow?
Octet. Because if you
All of them. I see what you're saying with octet. I apologize. That is fair. Okay. The green atom comes in, you'd exceed the octet on that carbon, so that would explain the red arrow has to move away from the carbon. What else?
There's no pi bond in that step. All the oxygen.
There's still no pi bond in the next step.
But that's an octet issue.
So that's an octet if you're processing those electrons. So again, if you aren't processing those electrons, how else do you know that pi bond should move towards the oxygen?
It's more electronegative. That's the answer you're looking for, seriously?
It's that simple, yeah.
There's like 15 answers you can get to that.
Yes. Whoa, and that becomes the extra fun thing. There's a billion different ways you can get to the same conclusion. That what we're trying to address is all of those ways that you can think about to navigate these things. Okay? All of those should be at your fingertips. Which one you use is entirely up to you, and that's going to come down to your comfort with which pathway you're taking. But we need to be aware of all of those potential pathways. Okay? So cool, we've added two curved arrows, but we still didn't answer the question. We need to label the species as nucleophile, acid, base, or electrophile. I'll actually give Anthony credit here. I believe you said the nitrogen had to act as a nucleophile, and I just didn't write it down.
So then is the carbon from
The carbon's acting as an electrophile. You're like, I don't want to write out electrophile. Then don't write E. I'm not going to look at E and be like, is that base or electrophile? Because there's an E in the word base. E in the word idiot. You thinking about that one?
No.
Okay, what happens in the next step?
Acid base.
nitrogen.
I get it. You're processing a lot without talking through it. Say again?
The nitrogen proteins, H plus, and the negative oxygen.
I'm not following you at all. Sorry.
The nitrogen
Yeah.
loses a hydrogen.
Okay. So we break a bond.
Yes.
Okay, I
And
accept
then
that.
The negative oxygen then picks up.
And we gained a bond to the hydrogen there.
Yeah.
Right? So we could color code what's happening within those systems. Note that as we color code, what did I have to delete? The old color code from the previous step, because I don't want to be confused with what's happening within that. Okay? That gets challenging on a test, okay? But working through this here allows us to think through those processes, which would help us beef up our skills in those other methods that we use to identify what was changing. So how did that happen?
Nitrogen acting as an acid.
Yes, it is an acid-base reaction. The electrons from our oxygen, how, share with our hydrogen, which then causes the bond to break between the hydrogen and the nitrogen. Okay? So yes, this is an acid-base reaction, which means the labels should be.
Nitrogen as an acid, oxygen as a base.
Okay. I fully accept the oxygen as a base.
Hydrogen is.
And yeah, that's the nuance there. I would probably call the hydrogen an acid. If you circled the nitrogen, would I accept it? Yes.
Now,
I
we're
would.
going to get into this one.
Yeah,
Isn't
that's a
the
little
ni-
bit weird.
The nitrogen is donating the hydrogen.
It is.
Therefore, it's an acid.
Yeah.
Proton donator, proton acceptor.
But if you go through and say nitrogen is an acid, say
I'm
that in a vacuum, nitrogen's an acid.
Well, thank God
That's
we're not
not
in a
gonna work.
vacuum. If we were in a vacuum, then anything.
So
I say
it
is
only
okay.
works within this system, which is why I would argue it's okay. So if we move to the next one, this one becomes a little bit harder because what are we moving to? We're like, well, the structure is not
Bottom
there.
left.
And we could say, well, we're moving to the bottom left. Oh, I didn't do it for this one. Okay, I have adjusted this in the past, recognizing that seeing multi-line is not necessarily easy, so I duplicate the structure and bring it down here so to run it again. Does that make sense? Okay. In that case, I didn't duplicate it. We're now split lines. We got to deal with it. Okay, so what changed?
And the hydrogen moved, so it's another. Oh wait, this one's all. No, it's another acid base.
Okay. So hopefully we can see that that bond to our hydrogen was broken, and that bond to our hydrogen was formed. Okay. And you might be like, what I believe tripped you up was that there were some electrons that seemed to appear
Yeah,
and
exactly.
disappear
That's
at
exactly
kind of
right.
will. Okay, and we will come back to that in a second. Okay, and we're gonna have to push this a little bit faster, I think, which means again it's an acid-base reaction. Okay, what is our acid?
The oxygen connected to the tier.
And our base?
Won't accept as the H plus being an acid itself. It's what defines the acid.
Yeah, water, wet, and whatever. Okay, what's happening in the next system? The carbon-oxygen bond breaks to form our H2O. So if we're trying to highlight that oxygen, there it is.
And then lone pair from the nitrogen resonates to create a double bond.
Okay, we had that pi bond form. That pi bond formed from the lone pair that was unfortunately not drawn for us.
But wouldn't that make the nitrogen positive?
Lone pair, yes, it would. And what did we say? We are missing charges and lone pairs.
Yes.
Okay, again, trying to hide some of that chemistry so that you have to think through what's happening at those bond levels. Okay, so what do we say? This is a hard one to label because when we think nucleophile, acid-base, electrophile, you're talking about different species being acid-bases, nucleophiles, electrophiles. And in this case, is it different species? No, they're all within one system. Okay, that's confusing enough that don't label that structure. Okay, to me, I would lean towards the nitrogen acting as a nucleophile.
Oxygen acting as an electrophile.
Okay, and that this carbon is acting as an electrophile. But even that gets a little bit weird. Okay, but that's where I would kind of suggest it. Okay, if we move to the next system, our next reaction, oh, we got lots of stuff moving through here. We form the bond between the oxygen and the hydrogen. We form the bond, form the bond here. We form a bond here. What did we break? Bond there and a bond there. Okay. Oh, and we broke that.
It's just moved. So what would we say? Just that oxygen acts as a base because that's. Oh, and I suppose that no. I guess that one just acts as a base. Yeah.
Okay. This oxygen accepted a hydrogen,
Oh yeah, that too.
which makes it a base. This donated a hydrogen, which means it acted as
An acid.
an acid.
Electrons moving around doesn't really matter.
Okay. The rest of the electrons aren't changing the overarching chemistry, which was that we really just had this simple protonation, deprotonation, and that's all that really mattered. The rest of it, so if we're now to go through and label this reaction, is this an acid-base reaction? Acid-base, by definition, is only the transfer of a hydrogen. Did we only transfer a hydrogen? No, so it can't be acid-base.
Yes. Wait, but then.
Right.
Oh yeah, it does.
We started with one pi bond. We ended with 2. It's an elimination.
Well, I think the big part of that is also losing 2 sigma.
You could also go through and reference the amount of sigma that you went through and lost as well. In this case, I think you would be okay with that too. Okay. If we move to that last step, and we got to erase all of those pieces. What happened? We made the bond between the nitrogen and the carbon. We lost this pi bond, and we lost that.
Oh.
Yeah.
Oh, I see. And then the
So what
carbon
happened?
connected to the alcohol acted as a base. Okay, that last step is kind of tricky. Actually.
This is our acid. That's a base. Okay.
Wait, it says do not label that one.
The last one.
The last structure, there's nothing to go to. That's why you don't label
Oh,
it.
yeah, shit, yeah.
Okay. Which is neat. Vast majority of this was just acid-base chemistry. Okay. And if we look at that last reaction, it's actually just a straight up acid-base reaction. We didn't gain a pi bond, we just changed where the pi bond was located. So it's just an acid-base step. Okay. So within this context, again, thinking long distance, what are questions that I could ask? How can I be lazy?
You could change it instead of the nucleophile base acid electrophile, you could go with the, I don't remember the thing is, I don't know if it's the mechanism or the mechanism itself, I always get them confused, but elimination.
So, and this is where we'd have to be a little bit careful, because we're looking at mechanism here, we wouldn't run reactions, okay, so it wouldn't be elimination, it could be nucleophile elimination or electrophile elimination. So those are now the mechanistic steps. So you could go through and label the mechanistic steps. Yes, that's a good explanation. There were some parts that you struggled with. You struggled with some of those steps because what? What? No.
It's lying to us.
It's not that it was lying, it's that things were omitted.
A lie by omission, you ever heard of that before?
Fair play. It lied to you. Right? So what you could go through and do is look at it and be like, what are the things that were omitted all the way through this? Okay? What are the charges? What are the lone pairs? For us to determine acids and bases, what did we have to add to the structure to help us see that?
Charges.
And what's all the green stuff?
Arrows.
Arrows. You could add curved arrows. There's so many different layers of things that you could put on this question to fully understand or show an understanding and appreciation of what the definitions are for all of those individual pieces. Okay? Those are things that you can now go through and practice. One question gets you 4 or 5 different possibilities. That's what you should be thinking about when you attempt any practice exam. Okay? The only practice exam that you should ever get that is just the same as your test, okay, is from a really bad instructor. And 100% I accept that that's recorded. Okay? No instructor should give you the exact same test, physically in person, as they gave you as practice. That is utter nonsense. That shows absolutely nothing. Okay? With that excitement, we'll go ahead and end.